Imagine a storm. Not a storm of water or ice. Water ice. Imagine a storm so wild that it makes diamonds fall from the sky. It sounds like a myth. It sounds like a fairy tale. It sounds impossible. But it is not. This is science. In the far, cold reaches of our own solar system, this very thing could be happening right now. It is a story of immense pressure, ferocious lightning, carbon, on the giant gas planets. The rules of weather are completely rewritten. The results are more spectacular than any treasure hunter's wildest dream. The claim is shocking. It feels like it breaks the laws of nature as we know them. Diamonds are precious on Earth because they are rare. They form deep within our planet's mantle, over millions of years, under crushing force and intense heat. The idea that they could simply rain down from churning clouds seems absurd. Yet, the universe is a place of extremes. The conditions on planets like Saturn and Jupiter are so far beyond our everyday experience. What seems like fantasy here might just be ordinary physics over there. The sky is not a gentle blue blanket. It is a violent, multi-layered factory. This is not just a wild guess or a science fiction plot. For decades, planetary scientists have been piecing together a puzzle. Looked at the composition of giant planets' atmospheres, measured incredible pressures and temperatures deep within them, observed colossal lightning storms that dwarf Earth's. When they put those pieces together, a strange and beautiful picture began to emerge. Carbon soot, forged in the upper atmosphere, falling into a deep planetary furnace, crushed into pure, hard diamond. The story hangs on a simple, powerful hook. What if the most valuable gems on our world are just a form of precipitation on another? It forces us to reconsider what we think of as weather and value. A detective story played out across hundreds of millions of miles with powerful telescopes, robotic probes, brilliant laboratory experiments. From the familiar flash of lightning to the alien chemistry of a hydrogen-helium world, down into a crushing depth where the very definition of matter begins to blur. Prepare to have your perspective shifted. Imagine that. To understand how a planet can rain diamonds, you must first understand the planet itself. Saturn and Jupiter are not like Earth. Saturn, Jupiter. They are gas giants. Their atmospheres are immense, deep, and layered with strange chemistry. Unlike our own nitrogen, oxygen, air, their skies are made mostly of hydrogen, helium. But floating within that vast ocean of gas are other crucial ingredients. Most important for our story is methane. Methane is a simple molecule, one atom of carbon bonded to 4 atoms of hydrogen. It is the source of the diamonds. The storms on these planets are monsters. On Earth, a big hurricane might last for a couple of weeks and span a few hundred miles. On Jupiter, the Great Red Spot is a storm that is wider than our entire planet and has been raging for centuries. These tempests are driven by the planet's rapid rotation and the intense heat bubbling up from their deep interiors. They generate winds that blow at hundreds of miles per hour and create lightning bolts that are thousands of times more powerful than anything we experience. This isn't just weather, it is a planetary engine of unimaginable scale and violence. Think of the atmosphere as a series of layers, each one different from the one above it. High up, you have wispy clouds of ammonia ice. Deeper down, there are clouds of ammonium hydrosulfide, and even deeper still, clouds of water ice. The pressure and temperature increase dramatically as you descend. It is like diving into an ocean, but an ocean made of gas that gets thicker and hotter with every mile you go down. The pressure at the top is gentle, but thousands of miles below, it becomes millions of times greater than the air pressure on Earth's surface. This incredible pressure gradient is the key. It is this combination of ingredients and conditions that sets the stage for diamond rain. You need a source of carbon, which you get from methane. You need a trigger to release that carbon, which you get from the massive lightning strikes. And you need an immense natural press to squeeze that carbon into a crystal structure, which you get from the crushing weight of the thousands of miles of atmosphere above. On Earth, we have some of these elements, but not at the sheer scale or intensity found on a gas giant. The giants are the perfect cosmic laboratories for this exotic process. Yeah. The story of a falling diamond begins with a flash of light. In the turbulent upper atmosphere of Saturn or Jupiter, a superbolt of lightning rips through the methane-rich clouds. This is not a gentle spark. It is an energetic event that carries enough power to shatter molecules. The lightning strikes the methane and breaks the chemical bonds holding it together. The hydrogen and carbon atoms are torn apart. The hydrogen, being a light gas, can float away and rejoin the surrounding atmosphere. But the carbon is different. It is left behind, free and unattached. These newly freed carbon atoms are reactive. They quickly begin to stick to each other. At first, they form long, stringy chains. Then those chains clump together into what scientists call soot. Think of it like the black, powdery carbon from a fireplace or candle flame. Huge plumes of this dark soot are created in the wake of the giant storms. Because soot is heavier than the surrounding hydrogen and helium gas, it does one thing: it falls. As the soot drifts downward, it sinks deeper into the planet's atmosphere. With every mile, pressure from the overlying gas increases relentlessly. Temperature rises too, climbing to thousands of degrees. The loose, disorganized soot cannot withstand this assault. Carbon atoms get squeezed together with immense force. They rebond and rearrange into a more stable, compact form. Soft powder is compressed into the hardest substance known. Under the right conditions, about 100,000 times Earth's atmospheric pressure, the transformation completes. Carbon atoms lock into a perfect 3D crystal lattice. The soot has become diamond. These are not giant, cut gemstones. At first, they're tiny nanocrystals, smaller than a grain of sand. But they are true diamonds, and they continue to fall, a steady, glittering shower through the deep atmosphere. A rain of precious gems born from lightning and soot, deep inside a world we can only watch from afar. Fascinating. This incredible story of diamond rain would remain pure speculation if not for the power of laboratory science. We cannot send a probe deep into Saturn to scoop up a sample, so scientists had to bring the conditions of Saturn to Earth. In cutting-edge facilities, researchers use powerful tools to simulate the hellish environment inside a gas giant. One of the most famous experiments took place at the SLAC National Accelerator Laboratory, where scientists used a laser called the Linux Coherent Light Source to create mind-boggling pressures for a fraction of a second. The experiment was both simple in concept and breathtaking in execution. Researchers started with a material that mimics the chemistry of the gas giant's atmospheres, such as polystyrene, which is a plastic made of hydrogen and carbon. They then fired incredibly powerful laser beams at a tiny sample of this material. The laser created a shock wave that blasted through the plastic. For a few nanoseconds, this shock wave compressed the material, generating pressures millions of times greater than Earth's sea-level atmosphere and temperatures reaching thousands of degrees Celsius, a near-perfect imitation of the conditions about 6,000 miles deep inside Saturn. The results were astonishing. As the shock wave passed through, it broke apart the plastic, separating the hydrogen and the carbon. The immense pressure then squeezed the carbon atoms so hard and so fast that they instantly reformed into tiny diamond crystals. The scientists were able to use the LCLS's ultra-bright X-rays, acting like a super-fast camera, to watch this transformation happen in real time. They saw the carbon atoms snap into the classic diamond structure in less than a billionth of a second. It proved that diamond formation does not necessarily need millions of years. Under the right, violent conditions, it can be nearly instantaneous. This laboratory evidence was a game changer. It moved the idea of diamond rain from the realm of plausible theory to scientifically supported phenomenon. The experiment demonstrated that the fundamental physics works. If you take carbon and subject it to the pressures and temperatures found inside Jupiter-Saturn, it will form diamonds. While the lab-made diamonds were minuscule, the experiment confirmed the core of the hypothesis. It provided the physical proof that the strange weather report from the outer solar system was not just a fantasy. It was grounded in real, observable chemistry and physics. Well, Yeah, amazing. While lab experiments prove the basic principle, the true complexity of diamond rain comes to life inside a supercomputer. Scientists create sophisticated computer models. They simulate the atmosphere of Jupiter. They simulate the atmosphere of Saturn. These models are not just simple calculations. They are virtual planets. Atmospheric composition, temperature gradients, pressure changes, effects of massive storms. By inputting the known laws of physics and chemistry, researchers can release virtual carbon soot into the upper atmosphere and watch what happens as it falls. These simulations help fill in the gaps experiments and observations cannot yet reach. The models have revealed fascinating details. For instance, they suggest that Saturn might be a better place for diamond rain than Jupiter. The reason lies in their different temperature profiles. Saturn is slightly cooler at the relevant depths. Jupiter is hotter in those layers. On Saturn, the falling diamonds would remain solid as they sink through a vast region. On Jupiter, the conditions might cause diamonds to melt into a liquid carbon sea sooner. Saturn could have a steady, hail of solid diamonds falling to much greater depths. Jupiter might feature a more complex cycle of melting and refreezing. Furthermore, these simulations can explore the potential size of the diamonds. They start as tiny nanocrystals. As the hailstones fall through the dense atmosphere, they could collide and merge, growing larger. Some calculations predict after thousands of miles they could reach pebble size, or up to a centimeter. Imagine a sky where glittering rocks of pure diamond fall like hail, sinking ever deeper. These models also help explain a long-standing mystery. Observations show Saturn's upper atmosphere is surprisingly depleted of carbon. The theory of diamond rain provides a perfect explanation. If carbon is converted into soot and then into diamonds that fall into the interior, it is removed from the upper layers. Models that include diamond formation show a carbon depletion, matching our probe measurements. That alignment between model prediction and real-world data is powerful evidence the process is happening. Please subscribe to our channel for more deep dives into cosmic wonders. Like this video if the thought of a diamond storm blows your mind. And share it with someone who appreciates that the universe is stranger and more beautiful than we can imagine. Let us know in the comments, what other impossible weather do you think could exist on alien worlds? You might be thinking, this is a cool story, but why does it matter? It is not like we can go mine those diamonds. The significance of diamond rain goes far beyond the image of falling jewels. It fundamentally changes our understanding of how giant planets work. Planets are not just static balls of gas, they are dynamic systems. The movement of elements and energy within them determines their evolution, their temperature, even their magnetic fields. Diamond rain is a powerful mechanism for moving a key element, carbon, from the outer layers to the deep interior. Visual reference. This process has a profound effect on the planet's internal heat engine. As the heavier diamonds fall, they release gravitational potential energy, which is converted into heat. This diamond heating adds to the planet's overall energy budget, warming its interior. This extra heat source can help explain another puzzle. Why planets like Saturn radiate more heat into space than they receive from the sun. The slow, steady sinking of trillions of tons of diamonds generates a significant amount of warmth, contributing to the planet's internal glow and influencing the powerful convection currents that drive its violent weather. If this idea of falling diamonds is sparking your curiosity, imagine what other mysteries the universe holds. Take a moment to support the journey of discovery. Please subscribe to our channel for more deep dives into cosmic wonders. Like this video if the thought of a diamond storm blows your mind. And share it with someone who appreciates that the universe is stranger and more beautiful than we can imagine. Let us know in the comments, what other impossible weather do you think could exist on alien worlds? Your engagement helps us bring these incredible stories to more people. The movement of diamonds could also influence the planet's structure. Over billions of years, a massive amount of carbon could accumulate in a layer deep inside the planet. This could create a distinct boundary, or even a solid shell of diamond surrounding the core. Such a layer would affect how heat escapes from the core and how material flows in the planet's deepest regions. Understanding this helps scientists build more accurate models of what the unseen interiors of these giant worlds look like. It is like using a strange form of weather to perform geological survey from hundreds of millions of miles away. The journey of a diamond does not end when it forms. It has thousands of miles still to fall into regions of even more extreme pressure and temperature. What happens to these falling gems in the deepest parts of the planet? The answer depends on the planet. On the slightly cooler Saturn, the diamonds might stay solid for a very long descent. But eventually, even the hardest substance in the universe must meet its match. At depths approaching the planet's core, the temperatures soar to over 10,000 degrees Celsius, and the pressures are tens of millions of times that of Earth's. Under these unimaginable conditions, the diamonds would finally melt. They would transform from a solid crystal into a sea of liquid carbon. Imagine an ocean of molten diamond, sloshing deep in the heart of a gas giant. This liquid carbon would be denser than the surrounding metallic hydrogen, so it would continue to sink, eventually pooling around the planet's central rocky core. Over the age of the solar system, this could form a thick, globe-spanning layer of liquid carbon, a hidden ocean of what was once a glittering rain. This is a planetary feature unlike anything on Earth. There's an even more exotic possibility. Some scientists theorize that at the extreme pressures near the very center, the liquid carbon might be compressed into an even denser form of matter. The core of a gas giant is one of the most mysterious places in the solar system. We believe it is a mix of rock exotic ices, but the addition of a massive layer of carbon would dramatically change its composition and properties. The diamond rain is not just a weather phenomenon. It is a mechanism for building a planet from the top down, fundamentally altering its core. This brings us to a strange and dramatic twist involving the planet's magnetic field. Deep inside Jupiter and Saturn, the immense pressure transforms hydrogen gas into a liquid metal. This metallic hydrogen is electrically conductive and swirls with massive convection currents, generating the planet's powerful magnetic fields. If a rain of solid diamonds exists within this region, it could disrupt or modify those currents. Or if a sea of liquid carbon exists within this region, it could create complex electromagnetic interactions. The diamonds, being electrical insulators, could affect the flow, while a liquid carbon sea could create its own electromagnetic effects. The tiny gems falling from the sky could, in effect, be shaping the giant magnetic bubble that shields the planet from solar wind. For all the compelling lab evidence and computer models, we must maintain a healthy scientific skepticism. We do not have a video of diamonds falling on Saturn. We have not yet sent a probe tough enough to survive the descent and report back. Our evidence is strong, but it is indirect. The science rests on a tripod of theory, laboratory, simulation, remote observation. Each leg of that tripod is solid, but we are always searching for the smoking gun, a direct, unambiguous piece of proof from the planets themselves. Our best eyes on the outer solar system have been robotic explorers. The Cassini mission, which orbited Saturn for 13 years, gave us an unprecedented look at Storm's atmosphere rings. Its instruments measured atmospheric composition temperatures, lightning activity. The data Cassini sent back, particularly regarding the carbon depletion in the upper atmosphere, provides strong circumstantial evidence that supports the diamond rain hypothesis. Similarly, the Juno spacecraft, currently orbiting Jupiter, is mapping its magnetic and gravitational fields with incredible precision, giving us clues about the planet's deep interior structure that can be compared against models with and without diamond formation. The story might get even more dramatic as we look further out. The smaller ice giants, Uranus, Neptune, are also prime candidates for diamond formation, and perhaps on an even grander scale. These planets are richer in methane, other carbon compounds. Some research suggests that the conditions inside them are so favorable that diamonds could not only form but remain solid all the way down to the core. A few bold hypotheses even speak of diamond seas, diamond bergs, floating in a dense fluid mantle. It is a tantalizing idea that pushes the concept from a rain to a permanent geological feature. So, what is next in the search for proof? Future missions to the gas and ice giants could carry more advanced instruments designed specifically to look for the chemical signatures of this process. A probe that could survive a deeper plunge into the atmosphere could measure the transition of carbon from soot to diamond. Advances in seismology, studying how planet quakes ripple through a planet, could one day allow us to map the interior layers and detect a potential diamond or liquid carbon shell. For now, the thrill is in the chase. Let's step back from the science and simply marvel at the image. Out there, in the cold and darkness of space, on a world so large it could swallow our own 1,000 times over, it may be raining jewels. A storm not of water, but of shimmering carbon crystals, falling silently through a crushing atmosphere of hydrogen. Born in a flash of lightning fall as glittering dust grow into pebbles, finally melt into a hidden ocean billions of years old. This is not a myth. This is not a dream. This is a possibility grounded in the laws of physics. This story teaches us a profound lesson about the universe. It reminds us that our earthbound experience is just one tiny data point in a cosmos of infinite variety. The processes that we consider exotic or impossible may be commonplace under different conditions. What we value as rare and precious here may be just a form of weather elsewhere. It challenges our imagination and forces us to be humble. We are just beginning to understand the strange and wonderful chemistry that can unfold on other worlds, and each new discovery shows us that the universe is far more creative than we ever thought. The thought stays with you. It is a powerful mental image. Imagine standing on one of Saturn's icy moons like Enceladus, looking up at the colossal ringed planet hanging in the black sky. Swirling bands of its clouds, the faint glow of its aurora, the colossal shadows of its rings deep within those clouds. Silent, violent, beautiful soot is turning to sparkle. A tempest is producing treasure. Pressure, heat, the most common of elements. If you found this journey into the heart of a storm incredible, please help us share the wonder. Like, share, subscribe. What do you think a rain of diamonds would sound or feel like? Leave your most imaginative description in the comments below. In the end, we are left with a shocking and beautiful idea. Diamonds falling from the sky. Weird, real, possible. The cosmos may be far richer and stranger than our wildest dreams.